Our picture of the cosmos is about to be torn apart. We are on the verge of discoveries so profound they will rewrite every science textbook in existence. This is not a distant dream, but the direct result of 30 specific space missions now underway or on the drawing board. These are not just rockets and robots. They are master keys designed to unlock the universe's most guarded secrets, from the first glimmer of starlight to the hidden oceans of alien moons, and even the nature of reality itself. By the end of this journey, you will know the exact missions that could deliver the first proof of life beyond Earth within your lifetime. We will peer into the heart of a metal world that should not exist and listen for the echoes of colliding black holes from the dawn of time. What does it feel like to stand at the edge of such a monumental shift in understanding? We begin with the mission that has already cracked open the sky. The James Webb Space Telescope is not merely an observatory. It is a time machine. Orbiting 1,000,000 miles from Earth, it sees the universe not in visible light, but in the glow of heat in the infrared. This allows it to do something magical. It can look past the veil of cosmic dust and see the faint, stretched light from objects so impossibly far away that their light has been traveling to us for almost the entire age of the universe. Webb is staring back over 13.5 billion years, to a period just a few 100 million years after the Big Bang itself. It is capturing the birth cries of the very first stars and galaxies, entities that should, by all our old models, have been too small and too dim to see. And yet, there they are. Webb's first deep field image revealed galaxies that were too massive, too mature, too soon. This single observation has sent cosmologists back to their chalkboards, forcing a profound question. Did the universe get started much faster than we ever thought possible? But Webb's revolution is not confined to the ancient past. Its other great power lies in its ability to dissect the light from distant worlds. When an exoplanet passes in front of its host star, a sliver of that star's light filters through the planet's atmosphere. Webb can catch that sliver and break it into a spectrum, a chemical barcode. Within that barcode are the telltale signs of what that air is made of. The telescope is hunting for biosignatures, combinations of gases that, on our planet, are produced by life. The simultaneous presence of oxygen and methane, for instance, is a powerful signal, as these gases react and destroy each other unless something is constantly replenishing them. Something like biology. Its prime target is the TRAPPIST-1 system, a compact family of 7 Earth-sized worlds orbiting a cool red dwarf star 39 light-years away. Several of these planets sit in the star's habitable zone, where temperatures could allow for liquid water. Webb is now meticulously analyzing each one, sniffing their atmospheres for signs of water vapor, carbon dioxide, and those tantalizing biosignatures. It is a direct, methodical search for an answer we have sought for millennia. And while it looks outward, it also turns its gaze to our own celestial backyard, studying the atmospheres of moons like Saturn's Titan with stunning clarity, revealing weather patterns on a world with rivers of methane. Every new image, every new data point, is a piece of a puzzle so vast we are only now beginning to see its edges. This single mission, already operational, is actively dismantling old assumptions and building the foundation for the next great discovery. What if the first chapter in the story of alien life is being written not by a rover in the Martian dust, but by a telescope reading the color of a sunset on a world 40 light-years away? The galaxies Webb sees in its deepest stares are cosmic infants, yet they appear shockingly grown up. These sprawling collections of stars, seen as they were when the universe was a mere 3% of its current age, possess a mass and structure that our best simulations struggle to explain. It is as if we opened a family album expecting to see blurry pictures of toddlers and instead found fully formed adults staring back. This single observation from the deep field images suggests the early universe was a far more efficient and rapid star forge than anyone predicted, forcing a fundamental rewrite of how cosmic structures first assembled themselves from the primordial darkness. The very timeline of galaxy formation is now in question, hinting that the seeds of giants like our own Milky Way were planted impossibly early. While it rewrites the past, Webb is also conducting a forensic examination of alien skies in the present. One of its most tantalizing targets is a distant world called K218b, a so-called Hycean planet over 8 times the mass of Earth, orbiting within the habitable zone of its star. When Webb analyzed the starlight filtering through this world's atmosphere, the chemical barcode told a startling story. The data strongly suggests the presence of carbon dioxide and methane, a combination often linked to watery worlds. But the most electrifying and contentious hint was a potential signal for dimethyl sulfide. On Earth, this molecule is only produced by one thing, life, specifically by marine phytoplankton. The detection is not yet confirmed, and the scientific community is rightly cautious, debating the data and calling for more observations. But the possibility alone sends a tremor through everything we know. We are not looking at a simple, barren rock. We are looking at a world that may harbor a vast, global ocean beneath an atmosphere that might, just might, carry the faint chemical whisper of a biological process. A confirmed discovery would be the single most important scientific revelation in human history. It would instantly transform K218b and every world like it from a point of light into a place. The philosophical and existential shockwaves would be profound, answering the ancient question of whether we are alone in the universe with a resonant, universe-shaking no. It would mean life is not a miraculous accident confined to our pale blue dot, but a common feature of a cosmos rich with chemistry and potential. It would force us to confront a new reality, that we live in a galaxy that is not just habitable, but perhaps abundantly inhabited. The James Webb Space Telescope is holding a key to that door, and with every new observation, its hand is turning the lock. But the search for life is not confined to distant suns. It is also a boots-on-the-ground endeavor, and our own moon is about to become the most important science outpost in the solar system. This is the core of NASA Artemis program, a monumental undertaking with a simple, staggering goal: to return humans to the lunar surface, and this time to stay. Artemis is not a rerun of Apollo, where Apollo was a series of brief, flag-planting expeditions. Artemis is about building a foundation for permanent human presence beyond Earth. The architecture is a masterpiece of modern engineering. First, a small space station called the Gateway will be assembled in orbit around the Moon. Think of it not as a destination, but as a waypoint, a reusable command module and docking hub where astronauts can transfer from their deep space capsule, the Orion, to a lunar lander. From Gateway, they will descend to the surface, targeting a region no human has ever visited, the lunar South Pole. Why there? Because scientific probes have confirmed that deep within permanently shadowed craters, where sunlight never reaches, lie vast deposits of water ice. This discovery changes everything. Water is not just for drinking. It is a resource that can be split into hydrogen and oxygen, the very components of rocket fuel. This means the Moon could become a cosmic gas station, allowing spacecraft to refuel for journeys deeper into space. The long-term vision is Artemis Base Camp, a sustainable habitat where crews could live and work for months at a time. They would conduct unprecedented geology, study the effects of long-duration spaceflight on the human body, and test the technologies we will need to survive on Mars. Every piece of equipment, from new spacesuits designed for lunar dust to closed-loop life support systems that recycle air and water, is a prototype for the Red Planet. And the crew itself will make history as Artemis promises to land the first woman and the first person of color on the moon. This is not just symbolic, it is essential. A future that belongs to all of humanity must be built by all of humanity. The lessons learned on this dusty proving ground, just 3 days from home, will be the manual for our first footsteps on another world millions of miles away. The moon is no longer a finish line, but a starting gate. That water ice is more than a scientific curiosity. It is the cornerstone of a new space economy. The process is called in situ resource utilization, a technical term for a beautifully simple idea, using what you find on another world to survive and thrive there. On the moon, it begins with mining those shadowed craters, extracting the frozen water, and then using solar power to split it through electrolysis. The result is liquid hydrogen and liquid oxygen, the most powerful combination of chemical rocket propellants we have. This transforms the entire economics of deep space travel. Launching fuel from Earth is phenomenally expensive, as every kilogram must be blasted out of our planet's powerful gravity well. But producing it on the moon, where gravity is only 1/6 as strong, means spacecraft could depart for Mars or beyond with tanks already full, having only had to lift the much lighter mining and processing equipment. The moon becomes a celestial pit stop, and Artemis Base Camp its first service station. This is not science fiction. Prototypes of these water processing reactors are already in development. The scientific payoff is equally profound. Those same permanently shadowed craters are cosmic deep freezes, preserving a record of the ancient solar system. The ice likely contains material delivered by comets and asteroids over billions of years, a pristine sample of the water and organic compounds that seeded the inner planets. By studying it, we are reading a history book of our own origins, one that has been locked away in lunar darkness since before life began on Earth. But to read that book, we must learn to live in an utterly hostile environment. The lunar surface is a vacuum, bathed in unfiltered solar and cosmic radiation, and subjected to extreme temperature swings. Surviving there for months is the essential dress rehearsal for Mars. Every system at Artemis Base Camp will be a test. How do we build habitats that shield astronauts from that radiation, using local soil or innovative materials? Can we perfect closed-loop life support where every drop of water and every breath of air is recycled with near-perfect efficiency? The psychological and physiological effects of a long mission in isolation, under the constant stress of a fragile artificial environment, must be understood here, where a rescue mission from Earth is only days away, not the many months it would take from Mars. Mastering these challenges on the moon is the only responsible path forward. It turns a monumental, perilous leap into a series of manageable, calculated steps. Each successful month a crew spends on the lunar surface, each tank of locally produced fuel, each experiment in growing food in regolith, is a solved problem that we will not have to face for the first time on a distant, red desert world. The moon is our training wheels for the solar system. The moon is a proving ground, but Mars holds the evidence. For decades, robotic emissaries have scoured its rust-colored plains, sending back data and images that have transformed it from a blurry red dot into a world of ancient river deltas and deep, salty lakes. They have found the chemical building blocks of life. But to answer the ultimate question, we need more than data. We need the rocks themselves. This is the audacious goal of Mars Sample Return, a mission so complex it is a planetary-scale relay race involving 3 separate spacecraft and 2 space agencies. It begins right now with a robot named Perseverance. Since its landing in Jezero Crater, Perseverance has been doing far more than taking breathtaking photos. Its core mission is forensic geology. It is drilling into the very bedrock of an ancient lakebed, a place where water once stood still for millions of years, collecting sediment and, just possibly, preserving the faintest traces of microbial life. With each core sample, a slender cylinder of rock about the size of a piece of chalk, the rover seals it inside a pristine titanium tube. Then, it does something remarkable. It places that tube on the ground, creating a carefully mapped cache of Martian treasure. Perseverance is the cosmic collector, the first leg in a relay that will span millions of miles and several years. The next step is a mission still on the drawing board, the Sample Retrieval Lander. This spacecraft will touch down with pinpoint precision near Perseverance's cache. It will carry 2 new pieces of technology never before seen on Mars. The first is a small fetch rover, designed to speed across the terrain, gather those cached sample tubes, and bring them back to the lander. The second is perhaps the most daring component of all, the Mars Ascent Vehicle. This will be the first rocket ever launched from the surface of another planet. The Fetch rover will load the samples into a basketball-sized container, which is then placed atop this slender rocket. On command, the ascent vehicle will ignite, punching the precious cargo up through the thin Martian atmosphere and into orbit. But the race is not yet won. Waiting in that orbit will be the third spacecraft, the Earth Return Orbiter, built by the European Space Agency. Its job is to spot the incoming sample container, rendezvous with it, capture it, and then seal it inside a robust biocontainment system. Only then, with the samples secured against the rigors of deep space and the possibility, however remote, of Martian material, will the orbiter begin the long cruise home. Years after the first sample was drilled, a small, charred capsule will finally streak through Earth's atmosphere and parachute into a desert landing site. Why go through all this unimaginable trouble? Because our terrestrial laboratories are wonders of detection. We have instruments far more sensitive and versatile than anything we can shrink down to fit on a rover. In these labs, scientists can slice the Martian rock into layers thinner than a human hair, analyze its atomic composition, and search for the subtle, textured patterns that are the fossilized signatures of microbial mats, patterns no rover camera could ever resolve. They can look for complex organic molecules arranged in ways that only biology produces. Mars Sample Return is not about finding a single smoking gun. It is about building an irrefutable case, with evidence examined by thousands of experts using the full power of human scientific ingenuity. A single, tiny tube of red dirt could contain the proof that life is not a singular miracle of Earth, but a natural process that arises wherever the conditions are right. It is the difference between seeing a shadow and holding the object that cast it. But retrieving a sample from Mars is a task measured in decades. What if the evidence of life is spraying into space right now, just waiting to be tasted? That is the breathtaking promise of a world orbiting Jupiter. Europa, one of the gas giant's largest moons, is a gleaming white marble crisscrossed with rusty red scars. Its surface is a shell of water ice, cracked and shifting over a hidden realm of profound significance. Beneath that frozen crust, scientists are virtually certain lies a global ocean. Not a small sea, but a body of water containing more than twice the volume of all of Earth's oceans combined. It is kept liquid not by the distant sun's feeble warmth, but by the relentless gravitational kneading of Jupiter itself. As Europa orbits, the immense pull of the giant planet flexes its interior, generating enough heat through tidal friction to maintain a vast, dark, salty sea against the cold of space. And where there is liquid water, an energy source, and the right chemistry, there is the potential for life. To investigate this alien abyss, NASA is building its most ambitious planetary science mission ever, the Europa Clipper. This sophisticated spacecraft, scheduled to launch in the coming years, will not orbit Europa directly. Instead, it will enter a looping orbit around Jupiter, designed to swing past Europa nearly 50 times over several years. Each flyby will be a high-speed reconnaissance pass, bringing the Clipper incredibly close to the icy surface to gather different types of data before it swings back out into the relative safety of space, away from Jupiter's punishing radiation belts. Its toolkit is a marvel of remote sensing. An ice-penetrating radar will send signals down through the crust, measuring the thickness of the ice and searching for pockets of subsurface water closer to the surface. A thermal imager will map temperature variations, looking for warm spots where the ocean might be melting the ice from below. But the most tantalizing instrument is its mass spectrometer. Previous observations from the Hubble Space Telescope have provided strong evidence that Europa occasionally erupts. Giant plumes of water vapor, possibly carrying material from the subsurface ocean, shoot hundreds of miles into space through cracks in the ice shell. The Clipper is designed to fly directly through the faint outskirts of these plumes. As it does, its mass spectrometer will act like a cosmic tongue, sampling the particles and instantly determining their chemical composition. It will be tasting the ocean without ever touching it. What will it find? Simple salts are expected, but the holy grail would be the detection of complex organic molecules, the carbon-based building blocks of life. Finding them in a plume would be a direct signal that the ocean below is not just water, but a rich, probiotic soup. It would tell us that the conditions for life are not only present but actively churning. The implications are staggering. A confirmed habitable ocean on Europa would instantly make it the most important world in the solar system after Earth. It would prove that the recipe for life can work in the darkest, most unexpected places, completely isolated from the sun's energy, powered instead by the geology of a moon. This would vastly expand the cosmic real estate we consider livable. Suddenly, the icy moons of Saturn, like Enceladus with its own spectacular plumes, and even the distant frozen worlds in the Kuiper Belt, become candidates. Life would no longer be a possibility tied to a star's Goldilocks zone, but a potential feature of any world with a heat source and liquid water. The Europa Clipper is a mission of profound existential reconnaissance. It is not going to find fish, but it is going to answer the most critical preliminary question: is the ocean of Europa a sterile chemical bath, or a nurturing, life-giving cradle? The answer will either confine our hopes for life to a few special planets or fling open the doors to an entire galaxy of hidden aquatic worlds. Europa's hidden ocean is a tantalizing mystery, but on another moon, the chemistry of life is not hidden at all. It is flowing in rivers and pooling in seas under an open sky. Saturn's largest moon, Titan, is a world of stunning and eerie familiarity, a funhouse mirror version of Earth. It is the only other place in the solar system with a dense atmosphere and stable bodies of liquid on its surface. But here, the rain is not water, it is liquid methane. The rivers carve valleys through water-ice bedrock, and the vast seas are composed of ethane and methane, sitting at a frigid minus 290 degrees Fahrenheit. This is a landscape built from the very organic compounds that are the precursors to life. To navigate this bizarre hydrocarbon wonderland, NASA is preparing an explorer unlike any other. The mission is called Dragonfly, and it is a nuclear-powered drone rotorcraft, essentially a large, sophisticated drone designed to be an aerial laboratory. Titan's thick atmosphere, 4 times denser than Earth's, and its low gravity make it an ideal world for flight. Dragonfly will use its 8 rotors to lift off, fly for tens of miles, and land at a new site of scientific interest, repeating this process over a mission lasting years. It is not a rover limited to one location. It is a flying scientist capable of sampling and comparing environments across a vast region, from the expansive dune fields of organic sand to the floor of an ancient impact crater where liquid water and organic materials may have once mixed. Dragonfly's core mission is to investigate probiotic chemistry, the complex chain of reactions that, on the early Earth, eventually led to the emergence of life. Titan's atmosphere is a giant, ongoing chemical factory. Sunlight and energetic particles from Saturn break apart methane and nitrogen molecules, which then recombine into increasingly complex organic compounds. These molecules, which scientists call tholins, rain down on the surface, creating a rich layer of organic sludge. Dragonfly will land in such an area, its instruments designed to taste the very building blocks. It will have a drill to sample the icy surface material, a mass spectrometer to identify the exact molecules present, and sensors to study the moon's geology and atmosphere. The question is not whether Titan has life today. Its surface is far too cold for biology as we know it. The question is whether we are watching the same chemical steps that unfolded on our own planet billions of years ago, frozen in time. By studying Titan's environment, we are essentially conducting an experiment on a planetary scale, observing what happens to organic chemistry over eons in the absence of life to consume it. Could the same complex molecules that became amino acids and proteins on Earth be lying in the dunes of Titan, waiting for a warmer era or a different catalyst? Dragonfly is a journey to a world that holds a possible blueprint for our own origins, a chance to understand the universal recipe that might turn chemistry into biology. What if the story of life on Earth began not in a warm little pond, but with ingredients that fell as a slow, cold rain on a world a billion miles away? Dragonfly will taste the chemistry of a world in deep freeze, but to understand the fate of the entire cosmos, we must map its invisible skeleton. This monumental task falls not to a spacecraft, but to a revolutionary new eye on the ground. Perched high in the clear, dry mountains of Chile, the Vera Sea, Rubin Observatory is preparing to begin the greatest celestial census ever attempted. Its mission is the Legacy Survey of Space and Time, a 10-year project that will not take a single snapshot of the universe, but an entire movie. Every few nights, its enormous mirror and 3.2 gigapixel camera, the largest digital camera ever built, will capture a panoramic image of the southern sky so detailed it could resolve a golf ball from 15 miles away. Night after night, year after year, it will repeat this process, compiling a time-lapse of the heavens. This is not about seeing farther, but about seeing everything and seeing it change. Over a decade, the LSST will catalog an estimated 20 billion galaxies and 17 billion stars within our own Milky Way. It will log everything from distant quasars to asteroids in our own backyard. But its true power lies in detecting motion and variation, the subtle flickers and shifts that reveal the universe's deepest secrets. It will spot millions of transient events, sudden, fleeting cosmic phenomena. This includes supernova, the explosive deaths of stars, which act as standard candles for measuring cosmic distances. By tracking thousands of these explosions at different distances, the survey will trace the expansion history of the universe with unprecedented precision, putting our theories of dark energy, the mysterious force accelerating that expansion, to the ultimate stress test. The observatory will also map the invisible scaffolding of the cosmos' dark matter. We cannot see dark matter, but we can see how its immense gravity bends the light from distant galaxies, a phenomenon called weak gravitational lensing. By meticulously measuring the subtle distortions in the shapes of billions of galaxies, the Rubin Observatory will create the most detailed map yet of where dark matter clumps and flows, revealing the hidden architecture upon which all visible reality is built. And its watchful eye has a very practical, earthly purpose. The survey will discover and track millions of asteroids, including an estimated 2/3 of all potentially hazardous near-Earth objects larger than a city block that come close to our planet's orbit. It is our early warning system for the solar system, a guardian cataloging the rocks that cross our path, from the fleeting flash of a dying star at the edge of time to the silent drift of a mountain-sized rock that could one day pass uncomfortably close, the Vera Sea. Rubin Observatory will connect the cosmic to the local. It is building a dynamic, living atlas of everything that moves, changes, or lurks in the dark, providing the raw data that could finally solve the twin mysteries of dark matter and dark energy that govern our universe's destiny. The Rubin Observatory maps the cosmos by watching light, but to hear the universe, we need an instrument of an entirely different kind. It listens not for photons, but for the subtle shudders in the fabric of reality itself. These are gravitational waves, ripples in spacetime first predicted by Albert Einstein over a century ago. Imagine the universe as a vast, still pond. When a massive object moves, like two black holes swirling together in a final, violent dance, it creates waves that travel outward at the speed of light, stretching and squeezing space itself as they pass. For decades, this was just a beautiful theory. Then, in 2015, ground-based observatories made the first historic detection, catching the final milliseconds of two stellar mass black holes colliding. It was a triumph, but it was like hearing only the crashing crescendo of a symphony. We were missing the entire slow-building overture. To hear that, we must go to space. That is the purpose of LISA, the Laser Interferometer Space Antenna. This is not a single telescope, but a constellation of 3 identical spacecraft, flying in a perfect triangular formation. They will be placed in an orbit that trails behind Earth, maintaining a staggering distance of 2.5 million kilometers between each craft. Connecting them will be laser beams, forming the most precise rulers ever conceived. The principle is exquisitely sensitive. As a gravitational wave passes through the triangle, it will minutely change the distance between the spacecraft by an amount far smaller than the width of a single atom. The lasers will detect this infinitesimal shift, allowing LISA to sense the wave's passage. By operating in the quiet vacuum of space, free from the seismic rumbles and thermal noise of Earth, LISA will tune into the low-frequency gravitational waves that are completely inaccessible from the ground. This is where the cosmic symphony truly unfolds. LISA's primary target is the merger of supermassive black holes. These monsters, weighing millions or even billions of times the mass of our Sun, lurk at the hearts of galaxies. When galaxies collide, their central black holes eventually spiral together over eons. This process generates a deep, rumbling gravitational wave signal that can last for years. LISA will hear these colossal events from across the universe, allowing us to sense these invisible giants and understand how galaxies assembled themselves over cosmic time. But the potential goes even deeper into the very first moments of existence. Some theories suggest that the violent birth of the cosmos in the Big Bang generated a background hum of primordial gravitational waves, a fossil imprint from the instant of creation itself. Detecting this signal would be like hearing the echo of the universe's first cry, offering a direct glimpse into conditions a fraction of a second after everything began. LISA opens a window to a universe we have never before perceived, one where we don't just see the objects, but feel the very space-time they warp and twist with their immense gravity. While LISA listens for the ripples from colliding giants, another mission is preparing to stare into the cosmic dark and map the void itself. The Nancy Grace Roman Space Telescope, named for the pioneering NASA astronomer often called the Mother of Hubble, is an observatory built for scale. Where Hubble and Webb are masters of deep, narrow fields, Roman is a surveyor of the grand panorama. Its wide-field instrument will capture images of the sky 200 times larger than Hubble's deepest views, but with the same stunning sharpness. This allows it to perform a monumental task, to take a cosmic census on an unprecedented scale, charting the positions and distances of billions of galaxies. Its primary target is not the light, but what the light reveals about the darkness. Roman is designed to tackle the twin enigmas of dark energy and dark matter. It will do this through three powerful techniques. First, by discovering thousands of distant supernovae, it will measure the expansion rate of the universe across cosmic time with finer precision than ever before, probing the accelerating push of dark energy. Second, it will observe the subtle distortion of galaxy shapes caused by dark matter's gravity-bending light, a phenomenon called weak lensing, creating the largest and most detailed map of the invisible cosmic web. And third, it will measure how galaxies cluster together over vast distances, another fingerprint of dark matter's gravitational influence. This trifecta of data will either confirm our current models of these mysterious forces or, more excitingly, reveal cracks in the foundation, pointing toward a new and deeper physics. But Roman has a second, equally revolutionary eye. Attached to the telescope is a groundbreaking technology demonstrator called a coronagraph. This instrument is a starlight suppression system, a high-tech shield designed to block the blinding glare of a host star so that the faint, reflected light of its orbiting planets can be seen. Think of it as using your hand to block the sun to see an airplane flying close to it. Roman's coronagraph will be the most advanced ever flown in space, aiming to directly image and analyze the atmospheres of giant exoplanets, Jupiter-sized worlds orbiting close to their stars. While it won't find Earth twins, its success is critical. It will prove the technology and techniques needed for the next generation of telescopes, those that will one day hold up their own hands to distant suns and capture the pale blue dot of another Earth. Roman is a bridge mission in the truest sense, connecting our current understanding of the cosmos's large-scale structure to the future moment we might see a world like our own shining in the darkness. The Roman Space Telescope will map the dark energies shaping our universe's fate, but to find the cradles of life, we must journey to a realm of profound and violent beauty. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, is already on its way, embarking on a daring 8-year voyage to perform the most comprehensive investigation ever of a gas giant and its mysterious ocean-bearing moons. Its destination is not just one world, but an entire miniature solar system in its own right, orbiting the king of planets. JUICE will spend years weaving through the gravitational tides of Jupiter, conducting close flybys of 3 extraordinary moons, Europa, Callisto, and the crown jewel Ganymede. This mission represents a fundamental shift in perspective. We are no longer studying single, isolated targets. We are analyzing an entire planetary ecosystem, understanding how the immense force of Jupiter and the complex interplay between its moons creates and sustains environments where life could potentially arise. Ganymede is a world of staggering superlatives. It is not merely Jupiter's largest moon. It is the largest moon in the entire solar system, bigger than the planet Mercury. It is the only moon known to generate its own magnetic field, a miniature version of Earth's protective bubble, created by the churning of a molten iron core deep within its interior. This magnetic field interacts with Jupiter's own far more powerful one, creating intense auroras around Ganymede's poles. But the most compelling secret lies beneath its icy, cratered crust. A vast, salty ocean is believed to exist there, sandwiched between layers of ice. JUICE is equipped to confirm this and probe its nature. Its suite of instruments includes a powerful ice-penetrating radar that will send signals deep into Ganymede, mapping the subsurface structure and directly measuring the thickness of the ice shell to locate the hidden water layer. A laser altimeter will map the moon's topography in exquisite detail, revealing how the surface flexes under Jupiter's gravity, which provides critical clues about the ocean's depth and the moon's internal structure. By studying Ganymede so thoroughly, JUICE aims to answer a pivotal question: can a moon with a metallic core, a magnetic field, and a subsurface ocean be considered a new class of planetary body, a marine world with its own distinct geophysical personality? Yet Ganymede is only part of the story. JUICE Grand Tour includes repeated flybys of the other ocean world candidates. It will sweep past the ancient, battered surface of Callisto, a moon thought to possess a subsurface ocean that may be in contact with a rocky seafloor, a potentially crucial interface for chemical reactions. And while NASA Clipper focuses intensely on Europa, JUICE will add crucial context with 2 dedicated flybys, gathering complementary data on its plume activity and surface composition. This comparative planetology is the mission's genius. By examining all 3 moons together, scientists can understand why they evolved so differently despite forming in the same neighborhood. Why does Ganymede have a magnetic field and the others do not? Why is Europa's surface so young and geologically active, while Callisto's is ancient and dormant? The answers lie in their interactions with Jupiter and with each other. The mission will also spend considerable time studying the gas giant itself, analyzing its complex atmosphere, its faint ring system, and its immense magnetosphere, a chaotic bubble of radiation and plasma that bathes the moons. This environment is both a shield and a threat, and understanding how these oceanic worlds persist within it is key to assessing their true habitability. JUICE is not just visiting moons, it is auditing an entire celestial dynasty, learning the rules that govern how such systems form, evolve, and possibly nurture the delicate chemistry of life in the dark. Venus is a planetary catastrophe, a world that took a horrifyingly wrong turn. While Mars whispers of lost oceans, Venus screams with a present-day fury, its surface hot enough to melt lead under an atmosphere of crushing carbon dioxide and sulfuric acid clouds. It is a vision of a runaway greenhouse effect pushed to the ultimate extreme. To understand this disaster, and to learn if our sister world was once a twin to Earth, NASA is sending 2 detectives with complementary skills. The DaVinci Plus mission is a daring atmospheric probe, an armored sphere designed to survive a 1-hour plunge through the thick, toxic shroud. It will not land, but during its descent, a suite of instruments will perform the most detailed chemical analysis of Venus's air ever attempted. It will measure the composition layer by layer, sniffing for noble gases like krypton and xenon, which act as forensic fingerprints of the planet's volcanic history and early water content. Most crucially, it will search for phosphine, a gas that on Earth is linked to biological activity, and whose tentative detection in Venus's clouds years ago sparked global debate. DaVinci Plus will settle the argument, determining if that signal was a mirage or a genuine mystery floating in the acidic haze. This descent is a journey back in time, reading the atmospheric record to piece together how Venus, likely born with similar ingredients to Earth, transformed from a potentially temperate world into a scorching pressure cooker. Its findings will be a stark warning, a detailed case study of climatic disaster on a planetary scale. But to read the full history, we must see the ground. That is the task of Veritas, an orbiting spacecraft equipped with a powerful synthetic aperture radar. Venus's permanent cloud cover has always hidden its surface from optical view. Veritas will pierce that veil, mapping nearly the entire planet with a resolution comparable to our best maps of Mars. It will not see a flat, dead plain. It will reveal topography in stunning detail, searching for the telltale signs of a lost, active world. Scientists will hunt for the wrinkled ridges and fractured plates of past tectonic activity, evidence that Venus, like Earth, once had a mobile, recycling crust. They will map ancient river valleys and possible ocean basins, looking for the geological scars left behind by flowing water billions of years ago. One of its most intriguing targets will be tessera, rugged, continent-like highlands that may be the oldest surviving crust on the planet. If these regions are made of granite, a rock that on Earth forms in the presence of water, it would be powerful evidence that Venus was not only wet, but had a geochemistry similar to our own world's continents. Together, DaVinci Plus and Veritas form a perfect investigative team. One samples the story written in the air, the other reads the ancient text carved into the rock. Their goal is to answer a haunting question that holds profound implications for every rocky world, including our own. Is Venus a cautionary tale of inevitable planetary doom? Or is it the ghost of a habitable paradise, a sister we lost to a climatic cataclysm long ago? The answer will define the thin line between a living Earth and a dead Venus. Venus reveals a story of planetary ruin, but to understand creation, we must find the original building materials. Deep in the asteroid belt between Mars and Jupiter, a strange, metallic world has waited since the dawn of the solar system. This is 16 Psyche, an object over 150 miles wide that appears to be composed almost entirely of iron and nickel. It is not a typical rocky asteroid. It is a survivor. The leading theory is breathtaking. Psyche may be the exposed, frozen core of a failed planet. In the violent early solar system, protoplanets collided and merged. Some grew into the worlds we know, while others were shattered. Psyche could be the naked heart of one of those primordial builders, stripped of its rocky mantle by colossal impacts billions of years ago. We have never seen anything like it. To visit this metallic relic, NASA has built a mission bearing its name. The Psyche spacecraft, launched in 2023, is on a multi-year voyage to rendezvous with this unique world. Once there, it will not land. Instead, it will enter orbit for a prolonged forensic examination. Its suite of instruments is designed to confirm the asteroid's metallic nature and map its history. A magnetometer will search for any remnant of a magnetic field, a ghost signal that would be the smoking gun proving this was once a molten, churning core. A multispectral imager will map the surface composition in detail, distinguishing between metal and any lingering rock. And a gamma-ray and neutron spectrometer will literally measure the elemental makeup of the surface, telling us the precise recipe of iron, nickel, and other metals. This mission is planetary archaeology. By studying Psyche, we are looking directly at a foundational piece of a planet that never was. It offers a chance to understand the violent processes of accretion and collision that built the terrestrial worlds, including our own Earth. We can only infer the properties of our planet's deep core from seismic waves, but at Psyche, we can visit one. The data could rewrite our textbooks on planetary formation, turning abstract models into observed reality. While Psyche investigates a single metallic world, another mission is embarking on a grand tour of celestial fossils from the opposite end of the solar system's history. This is Lucy, named for the famous fossil that illuminated human evolution. Its targets are the Trojan asteroids, two vast swarms of primitive objects that lead and follow Jupiter in its orbit around the Sun, trapped in stable gravitational pockets. These are not residents of the main asteroid belt. They are thought to be pristine leftovers from the outer solar system, icy and carbon-rich bodies that were captured by Jupiter's gravity during the giant planet's chaotic migration billions of years ago. Lucy's mission is unprecedented, a 12-year journey to visit a record-breaking 8 asteroids, 1 in the main belt and 7 Trojans. It is a single spacecraft on a celestial marathon, using Earth's gravity 3 times like a slingshot to reach these distant clusters. Each flyby will be a high-speed encounter, but Lucy's instruments are designed to work fast. Its color cameras and infrared spectrometer will capture the geology, composition, and surface features of each asteroid. The key question is one of diversity. Are all the Trojans made of the same stuff, or do they represent different classes of primordial material? Their compositions will tell us where in the early solar system they formed. Finding abundant dark, carbon-rich material and water-bearing minerals would indicate they originated in the cold realms beyond Jupiter, carrying with them the very organics and volatiles that may have later been delivered to the inner planets, seeding worlds like Earth with the ingredients for oceans and life. Lucy is collecting a sample book of solar system origins. By comparing these untouched fossils, it will help us reconstruct the earliest chapters of our planetary story, revealing how the giant planets shuffled the deck of building blocks and ultimately set the stage for a habitable Earth. Together, Psyche and Lucy are time travelers. One journeys to the iron heart of a lost protoplanet, the metal from which terrestrial worlds are forged. The other tours the icy, carbon-rich libraries captured at Jupiter's doorstep, the potential source of life's raw materials. They are missions to the beginning, seeking the foundational pieces from which everything, including us, was assembled. While Lucy tours the ancient Trojans, another mission prepares for a different kind of encounter, one that requires patience and perfect timing. The European Space Agency's Comet Interceptor is a mission built on a brilliant premise: to lie in wait for a visitor that has never been seen before. Its strategy is unlike any other. The spacecraft will launch not to a specific known target, but to a parking spot in space called the Sun-Earth L2 Lagrange point, a stable gravitational pocket 1 million miles behind Earth as viewed from the Sun. There it will remain in hibernation, a silent sentinel. Its purpose is to spring into action at a moment's notice. Astronomers are constantly scanning the skies, and should they discover a pristine long-period comet streaking inward from the distant Oort cloud, or even another interstellar object like the mysterious Oumuamua, they will sound the alarm. The comet interceptor will then fire its thrusters and embark on a high-speed rendezvous, designed to fly alongside the object as it makes its first, and likely only pass through the inner solar system. This is the critical distinction. Comets we have visited before, like Halley's Comet or Churyumov-Gerasimenko, are short-period comets. They have made countless loops around the Sun, their surfaces baked and altered by solar radiation, their volatile ices repeatedly boiled away. They are like books that have been left out in the rain, their pages faded and stuck together. A pristine long-period comet, however, is a different story. It may have spent billions of years in the deep freeze of the Oort cloud, a spherical shell of icy debris at the very edge of the Sun's gravitational influence. This is its maiden voyage into the warmth of the inner system. As the Sun's heat begins to touch it, it will erupt, but its underlying material will be virtually unchanged since the dawn of the solar system. The comet interceptor is designed to be there at that moment of awakening. The mission actually consists of 3 spacecraft in one, a main mothership and 2 smaller probes. They will approach the comet together, then separate to perform a coordinated flyby from different angles. This multi-point observation will create a revolutionary 3-dimensional profile of the comet's nucleus, its surrounding cloud of gas and dust known as the coma, and the interaction between the comet's material and the solar wind. The scientific payoff is a glimpse into the raw ingredients of our cosmic neighborhood. These ices and dust grains are the original building blocks from which the giant planets like Jupiter and Saturn coalesced. By analyzing their composition, we are reading the recipe written 4.6 billion years ago. Even more tantalizing is the mission's secondary target, an interstellar interloper. Since Oumuamua's brief visit in 2017, we know such objects pass through our system. The next one could be a comet from another star. Capturing data on its composition would be a sample of an entirely different planetary system, allowing us to compare the fundamental chemistry of our solar system with that of a neighbor light years away. The comet interceptor is a cosmic ambush, a patient hunter waiting for a piece of primordial history to fall into its lap. Its data could tell us not just where we came from, but how unique or how common our recipe for a solar system truly is. But to hear the faintest whispers from the dawn of time, we need an ear of unimaginable scale. The square-kilometer array is not a single telescope, but a continent-spanning network of perception. When its construction is complete, it will consist of thousands of radio dishes in South Africa and a forest of 1 million antenna stations in the remote outback of Western Australia. Together, they will form a single, colossal instrument with a total collecting area of, as the name suggests, 1 square kilometer. This gives it a sensitivity so profound it could detect an airport radar on a planet orbiting a star tens of light years away. Its primary mission is to listen for a signal that has been traveling for over 13 billion years, the faint radio hum from the cosmic dawn. This was the mysterious epoch, a few 100 million years after the Big Bang, when the first stars and galaxies ignited, burning away the fog of neutral hydrogen that filled the infant universe. The SKA is designed to detect the subtle fingerprint of that transformation, mapping the distribution of that primordial hydrogen as it was ionized by the first starlight. It will, in effect, produce a baby picture of the universe's first structures, showing us how the darkness first began to glitter. Beyond this monumental goal, the array will act as a galactic-scale laboratory for fundamental physics. It will monitor hundreds of ultra-precise cosmic clocks called pulsars, the rapidly spinning corpses of dead stars that emit beams of radio waves with metronomic regularity. By tracking the rhythmic ticks from this pulsar network across the galaxy, scientists can watch for infinitesimal variations. If a gravitational wave from a pair of supermassive black holes passes through our region of spacetime, it will minutely stretch and compress the distances between us and the pulsars, causing their ticks to arrive a fraction of a second early or late. The SKA will use this pulsar timing array to detect the low-frequency rumble of these monstrous collisions, creating a new way to sense the universe. And then, there is the most captivating possibility of all. In its relentless scan of the radio sky, the SKA will have the power to distinguish artificial signals from natural ones. It could detect the leakage from a distant civilization's own radio broadcasts, or perhaps an intentional beacon. While this search for technosignatures is a long shot, the telescope's sheer power means that for the first time, a negative result would be profoundly meaningful. If it hears nothing artificial across vast swaths of the galaxy, it would suggest that advanced, radio-transmitting civilizations are either exceedingly rare, incredibly brief, or have moved to a technology we cannot yet perceive. This quiet itself would be a deafening piece of data in the great puzzle of our cosmic solitude. The cosmos holds not only wonders, but also hazards. Drifting silently through the dark are mountains of rock and ice, remnants of the solar system's violent birth, and some of them cross Earth's path. The threat of an asteroid impact is not science fiction. It is a matter of geological record, etched into craters like the one beneath the Yucatan Peninsula that ended the age of the dinosaurs. To find these potential threats before they find us, NASA is building a dedicated sentinel for the sky. This is the NEO Surveyor, the Near-Earth Object Surveyor, a space telescope with one critical job: to discover and track the asteroids and comets that could pose a danger to our world. While ground-based telescopes do valiant work, they have a blind spot. They rely on reflected sunlight, which makes dark, carbon-rich asteroids incredibly difficult to see against the blackness of space. These are the stealth bombers of the solar system, absorbing most of the light that hits them. A NEO surveyor will hunt them in the infrared, sensing their faint heat signature against the cold background of the cosmos. Orbiting at a stable point between the Earth and Sun, it will systematically scan the sky, its infrared eyes tuned to pick up the warm glow of these dark objects. Its mandate is clear and urgent: to find at least 90% of all near-Earth asteroids larger than 140 meters, roughly the size of a football stadium, within the next decade. An impact from an object of that scale would not cause global extinction, but it would unleash regional devastation equivalent to thousands of nuclear weapons, flattening entire countries and altering the global climate for years. The difference between catastrophe and a close call is time. With its infrared advantage, a NEO surveyor is designed to give us that time, decades of advance warning for any object on a concerning trajectory. That warning is everything. With enough lead time, we are not helpless. Missions like NASA's recent DART experiment have proven the concept of planetary defense, showing that we can deliberately alter an asteroid's path by striking it with a spacecraft. Other ideas include using a spacecraft's gravity to gently tug an asteroid off course over years, or even painting one side of it white to let sunlight pressure slowly push it away. But all these deflection strategies require one thing we currently lack: a complete catalog of the threats. You cannot deflect what you cannot see. A neo-surveyor is the foundation of our planetary immune system, the early warning radar that allows us to see the danger coming with enough time to mount a response. It transforms asteroids from random acts of cosmic violence into manageable problems of orbital mechanics. Its mission is the ultimate act of foresight, a promise to future generations that we are watching the skies, not just in wonder, but in vigilance. The catalog of threats is being compiled, but the new frontier is already open for business. A quiet revolution is unfolding in lunar exploration, driven not by government flagships, but by private ambition. Companies like Intuitive Machines, Astrobotic, and iSpace are pioneering a new model, one of delivery and frequent access. Their spacecraft, with names like Nova C, Peregrine, and the Hakuto R lander, are not explorers in the traditional sense. They are cosmic couriers, designed to carry payloads for NASA, other space agencies, universities, and even artists to the lunar surface at a fraction of the historic cost. This marks a fundamental shift in how we operate beyond Earth. Where once a moon mission was a once-in-a-generation national endeavor, these companies promise regular, scheduled deliveries, turning the moon from a distant destination into a reachable worksite. Intuitive Machines made history with its Odysseus lander, becoming the first private company to achieve a soft landing on the moon. Its Nova C lander delivered scientific instruments to the lunar South Pole, a region of immense strategic interest. Astrobotic's Peregrine lander, despite facing critical propulsion issues on its maiden voyage, demonstrated the complex choreography of launching and navigating a private mission, providing invaluable data for its next attempt. Meanwhile, the Japanese company iSpace is iterating on its Hakuto R design, learning from a hard landing to refine its approach for future missions. Each flight, whether a complete success or a partial setback, is a rapid prototype in action, accelerating the learning curve through private enterprise in a way that traditional programs cannot. They are proving that commercial lunar logistics is not just possible, but operational. The payloads these landers carry are the seeds of a lunar economy. They are testing the core technologies needed for sustained presence. This includes precise landing sensors to touch down safely near valuable resources like water ice, new types of solar panels designed for the long lunar night, and experimental power systems. They are also conducting vital science, deploying seismometers to listen for moonquakes, analyzing the lunar soil or regolith to understand its properties for construction, and even testing novel farming techniques in sealed containers. Every instrument delivered, every experiment run, adds a piece to the puzzle of how to live and work on another world. These missions are building the foundational infrastructure, one small, commercially delivered package at a time. This new era fundamentally changes the economics of exploration. By creating a competitive market for lunar delivery services, NASA and other agencies can now purchase a ride rather than building the entire vehicle themselves. This allows them to focus their resources on the most complex, cutting-edge science and human exploration goals, while routine transport is handled by industry. It fosters innovation through competition, drives down costs through repetition, and dramatically increases the tempo of missions. We are moving from an age of monumental, one-off events to an age of lunar regularity. The moon is becoming a place you can ship a package to, and that simple, profound change is opening the door for everything that follows, from research outposts to resource mining. The frontier is no longer just a place we visit. It is a place we are beginning to supply. Statistical truth emerges not from a single, perfect example, but from 1,000 different stories. While the James Webb Space Telescope acts as a master detective, probing the deepest mysteries of individual worlds, another mission is preparing to become a cosmic sociologist, gathering data on an entire population. This is the European Space Agency's Ariel mission, the Atmospheric Remote Sensing Infrared Exoplanet Large Survey. Its purpose is beautifully simple, yet revolutionary in scope. Ariel will not focus on a handful of the most promising or bizarre exoplanets. Instead, it will conduct a uniform, systematic survey of the atmospheres of approximately 1,000 worlds, from scorching gas giants to smaller, warmer super-Earths, all orbiting close to their host stars. This is a mission built on the power of big data. For the first time, we will move beyond fascinating anecdotes and begin to understand the demographics of planets across our galaxy. How does a planet's composition relate to the type of star it orbits? What is the chemical diversity of atmospheres around different classes of worlds? Are water, methane, and carbon dioxide common features, or rare exceptions? By gathering this vast, consistent dataset, Ariel will reveal the trends and patterns that govern planetary formation and evolution. It will answer fundamental questions about the processes that shape these distant worlds. For instance, by comparing the atmospheric makeup of hot Jupiter's gas giants orbiting perilously close to their stars, to cooler giants further out, scientists can trace how intense stellar radiation strips away lighter elements or drives complex chemical reactions in the upper atmospheres. For smaller, rocky super-Earths, Ariel's survey could reveal how often these worlds manage to hold onto substantial atmospheres, and what those atmospheres are typically made of. Are they mostly hydrogen and helium, relics of their formation, or are they secondary atmospheres, outgassed from volcanoes or delivered by comets, rich in water and carbon compounds? This statistical approach is the key to understanding our own place in the cosmic story. We have one data point for a habitable, life-bearing world, Earth. But is it a statistical outlier, a 1 in a trillion miracle? Or is it a common, even inevitable outcome for a planet of its size and orbit around a star like our Sun? Ariel cannot detect life directly, but it can tell us how common the basic conditions for life as we know it might be. If it surveys hundreds of worlds in the super-Earth category and finds that a significant fraction have atmospheres showing signs of water vapor and temperate chemical balances, it would suggest that the ingredients for habitability are scattered liberally throughout the cosmos. Conversely, if most of these worlds show atmospheres that are barren, or choked in toxic gases, it would indicate that Earth's delicate balance is a far more precious and rare achievement. The mission achieves this by using a technique perfected by Hubble and Webb, but on an industrial scale. It will observe as planets transit, or pass in front of, their host stars. As the star's light filters through the thin ring of the planet's atmosphere, specific molecules absorb characteristic wavelengths of light. Ariel's specialized infrared spectrometer will dissect that filtered starlight for each of its 1,000 targets, creating a chemical barcode for their skies. It is a factory for atmospheric fingerprints. By the end of its 4-year primary mission, Ariel will have compiled the first ever comprehensive almanac of exoplanet climates. This catalog will be the ultimate guidebook for the next generation of telescopes. telling them exactly where to point their most powerful instruments in the search for biosignatures. It transforms the search for another Earth from a hopeful guess into a targeted investigation, grounded in the hard statistics of an entire galaxy of possibilities. Ariel will compile a galactic census of alien atmospheres, but one mission dares to propose a journey to actually touch them. The goal is not a neighboring planet, but a neighboring star. Breakthrough Starshot is perhaps the most audacious concept in the history of space exploration. A project that sounds like pure science fiction yet is backed by serious scientific minds and significant funding from the breakthrough initiatives. Its aim is staggeringly simple and staggeringly difficult: to send a probe to another star system within a single human generation. The target is Alpha Centauri, the closest star system to our own, a mere 4.37 light-years away. For a conventional spacecraft like Voyager, that journey would take over 70,000 years. Starshot's radical solution is to abandon the rocket entirely. Instead, the plan envisions launching a fleet of thousands of gram-scale probes, each no larger than a postage stamp, called star chips. These would be attached to a thin, reflective light sail, a square of material only a few meters across but thinner than a human hair. The propulsion would not come from onboard fuel, but from an immense array of ground-based lasers stationed on Earth. This phased laser array, spanning perhaps a square kilometer, would focus its beams on the light sails as they deploy in space, pushing them with the pure force of light photons. The acceleration would be gentle at first, but continuous. Over several minutes, this laser blast would propel the tiny sails to an unprecedented velocity, 20% the speed of light. At that pace, the journey to Alpha Centauri would take just over 20 years. The primary target within that system is Proxima Centauri b, an Earth-sized world orbiting within the habitable zone of its faint red dwarf star. The vision is for the fleet of star chips to scream past this alien world at breakneck speed, their miniature cameras and sensors snapping images and collecting data during the fleeting flyby, and then beaming that priceless information back to Earth. The scale of the challenge is almost beyond comprehension. Each star chip must be a complete spacecraft in miniature, carrying a camera, a power source, a communications laser, and a computer, all engineered to survive a 20-year journey through interstellar space and the punishing bombardment of cosmic radiation. The light sail material must be perfectly reflective, incredibly lightweight, and able to withstand the intense laser blast without vaporizing. Perhaps the greatest hurdle of all is communication. How does a 1-gram probe, 4 light-years away, send a signal powerful enough for us to detect? The plan relies on using the sail itself as an antenna, focusing a laser beam back toward our solar system. Even then, the signal would be incredibly faint, requiring a network of enormous receivers, possibly constructed in space, to have any hope of catching it. Every step involves technology that either does not exist today or exists only in laboratory prototypes. Yet, the project represents a fundamental shift in thinking. It asks, what is the smallest, fastest, cheapest thing we can send to another star? It embraces redundancy, sending thousands of probes knowing most may fail, in the hope that a few will succeed. Starshot is not a mission with a launch date. It is a century-long research and development roadmap, a challenge to the global scientific community to solve a series of monumental physics and engineering problems. Its ultimate success is uncertain, but its very conception changes the equation. It tells us that the stars are not forever out of reach, that interstellar travel may begin not with a mighty starship, but with a cloud of intelligent dust, pushed by a beam of light from home. Starshot's vision is a leap across light years, but another mission will make a profound discovery by looking at the entire sky, one color at a time. NASA SPHEREX, the spectrophotometer for the history of the universe, epoch of reionization and ICES Explorer, is a spacecraft with a beautifully simple yet staggeringly ambitious plan. It will not stare at a single galaxy or planet. Instead, it will slowly and methodically scan the entire sky, not once, but 4 times over its 2-year mission. And it will do this in 96 distinct color bands, from visible light out into the infrared. This is not about taking pretty pictures. It is about creating the most detailed cosmic map in history, a 3-dimensional atlas of the universe. Every point of light in its survey will have a precise color signature, and because of the expansion of the universe, that color tells us distance. The redder the light, the farther away the object and the further back in time we are seeing. SPHEREX will use this to construct a 3D model of billions of galaxies, charting their positions across billions of light years. This grand structure, the cosmic web, holds an echo from the universe's first split second. Scientists believe that during a period of hyper-expansion called inflation, just after the Big Bang, tiny quantum fluctuations were stretched to cosmic size, becoming the seeds for all future structure. The pattern of galaxies we see today is a frozen imprint of those primordial ripples. By mapping the distribution of galaxies with unprecedented statistical power, SPHEREX will test the theories of inflation with a rigor never before possible. It is like taking a fossilized footprint and deducing the weight, stride, and speed of the creature that made it. Only here the creature is the birth of spacetime itself. Yet while one set of instruments looks out to the edge of everything, another will turn its gaze inward, to the dusty, fertile nurseries within our own Milky Way. In the cold, dark clouds where new stars are born, simple molecules freeze onto specks of dust, forming icy mantles. These are not just water ices, but ices of carbon monoxide, carbon dioxide, methanol, and even more complex organic compounds. SPHEREX has a unique ability to detect the specific infrared fingerprints of these ices. As it scans the galaxy, it will survey these raw materials in stellar nurseries, creating a galactic inventory of the very ingredients that, when delivered to young planets by comets and asteroids, could seed them with the building blocks for oceans and life. It will tell us how common these prebiotic molecules are, and in what proportions they exist across different star-forming regions. Is our solar system's recipe typical, or were we born in an unusually rich chemical kitchen? SPHEREX connects the unimaginably vast to the intimately small. Its data will trace a line from the quantum jitters that shape the cosmos to the icy grains that may one day dissolve in the waters of an alien world. It is a mission of cosmic genealogy, asking one profound question: did the same ancient processes that arrange the galaxies also guarantee the chemistry for life? Its legacy is written across 3 decades of cosmic revelation. The Hubble Space Telescope, freed from the blurring effects of Earth's atmosphere, gave us a sharpness of vision that changed astronomy from a science of inference to one of direct observation. Its most profound contribution was not a single image, but a precise measurement that solved a century-old debate. By observing pulsating stars called Cepheid variables in distant galaxies, Hubble provided the key data that allowed astronomers to calculate the universe's expansion rate with unprecedented accuracy. This work didn't just tell us the cosmos was growing, it revealed the shocking acceleration of that growth, the first direct evidence for the mysterious force we now call dark energy. That single discovery alone rewrote the textbooks, but Hubble's gifts kept coming. It peered into the stellar nurseries of the Orion Nebula, showing us the swirling disks of gas and dust where planets are born. It chronicled the weather on other worlds, tracking giant storms on Jupiter and Neptune. And then, it performed an act of pure scientific audacity. Astronomers pointed it at a seemingly empty patch of sky, a dark void no larger than a grain of sand held at arm's length, and left its shutter open for 10 days. The result was the Hubble Deep Field, an image that contained not darkness, but a breathtaking tapestry of thousands of galaxies, each a smudge of light representing billions of stars, stretching back to the early universe. That single image transformed our perception of cosmic abundance, a humbling reminder that our entire Milky Way is but one island in an ocean of islands. Today, Hubble is far from a relic. It operates in a powerful partnership with the James Webb Space Telescope. While Webb sees the universe in the infrared, piercing dust clouds, and looking back to the first light, Hubble continues to provide the critical complementary view in visible and ultraviolet light. This tag-team approach allows scientists to see celestial objects in a fuller spectrum, like studying a painting under both natural sunlight and a blacklight to reveal hidden details. They work together to analyze the atmospheres of exoplanets, to dissect the aftermath of galactic collisions, and to trace the structure of the cosmic web. Hubble's longevity, maintained by daring servicing missions from the space shuttle, is its superpower. It has become a time-lapse camera on the universe, watching as a storm on Saturn grows and fades over years, or monitoring the slow brightening of a distant supernova. Its endurance means it can pursue questions that require patience, providing the baseline data that makes the snapshots from newer telescopes meaningful. In an age of technological marvels, this veteran observatory remains on the front line, its sharp eye still uncovering secrets, proving that the greatest discoveries are often made by the instrument that simply keeps looking. The legacy of Hubble is one of open skies and shared discovery, but the new era of space is also being written by nations with long-term, methodical ambitions. China's space program has executed a series of flawless, complex missions that have fundamentally altered the landscape of lunar exploration. It began with the Chang missions, named for the Chinese moon goddess, which progressed step by step from orbiters to landers with breathtaking speed. The crowning achievement so far is Chang 4, which accomplished a historic first no other nation has matched: a soft landing on the far side of the moon. Because the moon is tidally locked, one hemisphere forever faces away from Earth, making direct communication impossible. To solve this, China first launched a relay satellite Kuekiao to a special point in space beyond the moon, creating a communications bridge. Then, Chang 4 touched down in the von Karman crater within the South Pole Aitken Basin, the largest and oldest impact feature on the lunar surface. Its rover, Yutu-2, began exploring this terrain that had never been touched by human technology, analyzing soil and peering beneath the surface with ground-penetrating radar. The mission revealed that the far side's crust is strikingly different, thicker and more complex, offering clues to the violent impact history that shaped both Earth and its companion. But China did not stop there. Chang 5 followed, performing a dazzlingly complex robotic sample return from the moon's near side, bringing back fresh volcanic rock younger than any samples retrieved by the Apollo astronauts. This demonstrated a mastery of the entire chain of operations needed for interplanetary archaeology: launch, landing, sample collection, ascent from another world, orbital rendezvous, and return to Earth. The next steps are even more ambitious. Chang'e 6 is slated to attempt a sample return from the far side, aiming to bring back material from the ancient South Pole Aitken Basin, which could contain material from the Moon's deep mantle, blasted to the surface by the colossal impact. Chang'e 7 and 8 will then target the lunar South Pole, scouting for water ice and testing key technologies for sustained presence, like 3D printing with lunar soil. This leads directly to the grand vision, the International Lunar Research Station, a proposed partnership with Russia to establish a permanently crewed base on the Moon within the coming decades. This is not a symbolic outpost, but a planned hub for science, resource utilization, and as a proving ground for missions deeper into space. China's ambitions extend far beyond the Moon. Its first independent interplanetary mission, Tianwen-1, was a stunning success, delivering both an orbiter and the Zhurong rover to Mars on its first attempt. Zhurong explored the vast Utopia Planitia, using ground-penetrating radar to search for subsurface water ice and studying the Martian soil and climate. Now, the program looks to replicate its lunar sample return prowess on more distant targets. Tianwen-2 is a proposed mission to collect material from a near-Earth asteroid, while Tianwen-3 aims for the ultimate prize in robotic exploration, a Mars sample return mission, potentially in partnership with other nations. This methodical, step-by-step approach, from lunar orbit to the far side, from Mars rovers to asteroid sample returns, signals a profound shift. China is building a comprehensive, sustainable deep space exploration capability on a timeline measured in decades, not political cycles. They are positioning themselves not just as participants in the new space age, but as architects of its next major chapter, with the infrastructure and long-term plans to maintain a continuous human and robotic presence beyond Earth. The sky is no longer the domain of a single superpower, but a new frontier where multiple nations are writing their own destinies in the dust of other worlds. This methodical expansion into deep space is mirrored by a nation reaching for the stars from its own soil. India's space agency has charted a course from launching satellites to preparing for its most daring mission yet, sending its own citizens into orbit. The Gaganyaan program is a testament to decades of indigenous technological development, a 3-day crewed mission to low Earth orbit. The scale of this challenge cannot be overstated, as it requires mastering every critical system for human survival in the void. India has been meticulously checking off each box. They have developed a fully autonomous crew module, complete with life support and emergency abort systems. They have tested the powerful GSLV Mark III rocket that will carry it, and successfully demonstrated the crew escape mechanism, a tower that can pull the capsule to safety if the launch goes wrong. Perhaps most crucially, they have selected and trained a cadre of test pilots, sending them to Russia for advanced cosmonaut instruction. The national pride surrounding Gaganyaan is palpable, representing not just a scientific achievement, but a symbolic arrival on the world's highest stage. It promises to make India only the fourth nation capable of independent human spaceflight, joining an exclusive club and inspiring a new generation of engineers and scientists across the country. Yet, even as they prepare to send humans skyward, India has also launched a mission to stare directly into our star's fiery heart. The Aditya L1 Observatory is now stationed at a special gravitational parking spot between Earth and the Sun, a vantage point that allows it to observe our star continuously, without the interruptions of an Earth orbit. Its primary target is the solar corona, the star's wispy, superheated outer atmosphere. This region is a profound mystery, as it blazes at millions of degrees while the sun's visible surface below is a comparatively cool few thousand. How this atmospheric heating happens is one of solar physics' greatest puzzles. Aditya L1 is equipped with instruments to measure the corona's temperature, density, and magnetic fields in exquisite detail. But its mission has a deeply practical side as well. It will study the origins of solar winds, the constant stream of charged particles flowing from the sun, and monitor solar flares and coronal mass ejections, those gigantic eruptions of plasma and magnetism. When these violent outbursts are directed at Earth, they can trigger geomagnetic storms, dazzling auroras but also posing serious risks. They can overwhelm power grids, causing blackouts, disrupt satellite communications and GPS, and even endanger astronauts with heightened radiation. By improving our understanding of these solar tantrums, Aditya L1 contributes to the global effort to forecast space weather, giving us crucial time to protect our increasingly technology-dependent civilization. One mission lifts human ambition into orbit. The other guards our technological world from stellar fury, together marking India's arrival as a full-spectrum space power. The quiet pressure of sunlight is about to be harnessed for an epic voyage. NASA's solar cruiser is an experimental mission that dares to replace rocket fuel with the gentle, ceaseless push of light itself. At its heart is a solar sail, but this is no ordinary sail. When fully deployed in space, it will span an astonishing 1,650 square meters, an area nearly the size of an American football field. Yet the material is almost unimaginably thin, lighter than a single sheet of tissue paper, and coated to be highly reflective. The principle is elegant physics. Photons, the particles of light streaming from the sun, carry a tiny amount of momentum. When they strike the sail and bounce off, they impart that momentum to the spacecraft, giving it a continuous, gentle push. There is no combustion, no plume of exhaust, just the silent pressure of sunlight. The acceleration is minuscule at first, far less than the feeling of a single ant resting on your hand. But in the frictionless void of space, that push never stops. Day after day, week after week, the velocity builds, allowing a solar sail to reach incredible speeds over time, all without a single drop of conventional fuel. The solar cruiser mission is a crucial test of this technology at a grand scale. Its primary goal is to demonstrate navigation using this novel propulsion, steering by tilting the sail to catch sunlight at different angles, much like a sailor trims a canvas to catch the wind. Success would open the door to entirely new classes of missions that are difficult or impossible with traditional rockets. Imagine a spacecraft that could use its sail to hover at a unique point in space, not held by gravity, but balanced by the constant pressure of sunlight. Such a solar sentinel could maintain a fixed position relative to the sun and Earth, providing an uninterrupted, stable platform to monitor solar storms and give us earlier warning of space, whether that threatens our satellites and power grids. For deep space exploration, the implications are profound. A solar sail craft, once accelerated, could embark on missions to visit multiple asteroids or comets in the inner solar system with unprecedented efficiency, its journey limited only by the durability of its materials and the patience of its controllers. It is a technology of pure patience and momentum, turning the light that has warmed our planet for eons into the wind that will carry our probes to new frontiers. The silent pressure of light offers one path to the stars, but another search listens for a signal that someone else has already arrived. For decades, the quest for life beyond Earth has focused on biosignatures, the chemical traces of biology. Yet a parallel, equally profound search is gaining momentum: the hunt for technosignatures, the detectable evidence of advanced technology. This is not about finding microbes or algae, but about finding evidence of intelligence, of a civilization that has mastered its environment, perhaps even its star. The most traditional approach has been to scan the cosmos with radio telescopes, listening for the faint, artificial hum of a communication signal or a beacon, a deliberate or accidental broadcast from another world. Projects like SETI, the search for extraterrestrial intelligence, have for years analyzed millions of radio channels, using ever more sophisticated algorithms to sift through cosmic static for a pattern that screams of design. But the search is expanding beyond radio waves. Scientists now consider other potential markers, like the spectral signature of industrial pollutants in an exoplanet's atmosphere, the unnatural glow of city lights on a world's dark side, or even the telltale dimming of a star surrounded by a vast, energy-harvesting structure known as a Dyson swarm. This shift acknowledges that an advanced civilization might leave footprints far stranger and more varied than a simple radio hello. One of the most provocative new efforts is the Galileo project, led by renowned astronomer Avi Loeb. Its mission is to bring scientific rigor to the study of unidentified anomalous phenomena, objects in our skies that defy immediate explanation. Rather than relying on blurry military footage or anecdotal reports, the project is deploying its own suite of high-tech instruments, advanced cameras and sensors on mountaintops, designed to systematically observe and collect hard data on anything unusual that passes overhead. The goal is not to assume extraterrestrial origins, but to eliminate all conventional explanations with transparent, peer-reviewed data. If an object is found to exhibit physics beyond our current understanding, such as moving through the atmosphere without a sonic boom or performing maneuvers impossible for human technology, it would become a candidate for a potential technosignature right here in our own backyard. The philosophical weight of such a discovery is almost beyond comprehension. Detecting a biosignature on an exoplanet would tell us life is a natural cosmic process. But detecting a technosignature would answer a different, deeper question, one that has haunted humanity since we first looked up. We are not alone, and we are not the first. It would mean intelligence is not a fleeting spark in the dark, but a flame that can be kindled and sustained. The implications cascade through every aspect of our existence, from science and religion to our very sense of place in the universe. It would offer both a mirror and a warning, showing us a possible future for our own civilization, for good or ill. This is why the search for technosignatures is a legitimate, vital branch of astrobiology. It completes the picture. Biology may be the universe's way of creating complex matter, but technology may be its way of becoming self-aware. To search for one without the other is to tell only half the story of a cosmos that might be whispering, and perhaps even shouting, back at us. Their journeys began with a whisper of rocket fire in 1977. Two identical emissaries cast into the void on trajectories of staggering ambition. Voyager 1 and Voyager 2 were designed for a grand tour, a rare celestial alignment that allowed them to swing past the outer planets, using each world's gravity as a slingshot to propel them onward to the next. What they revealed was not the static, cratered worlds many had expected, but a solar system alive with violent beauty and impossible geology. Voyager 1's close encounter with Jupiter unveiled a complex, turbulent atmosphere, a swirling tapestry of storms larger than our entire planet. But the true shock came at its moon, Io. The images showed not an icy, dead sphere, but a world painted in garish yellows and oranges, its surface dotted with plumes. These were active volcanoes, driven by the immense gravitational tug of war between Jupiter and its other moons, making Io the most volcanically active body in the entire solar system. It was a world remaking itself in real time. Voyager 2 continued the tour, giving humanity its first close-up gaze at the ice giants, Uranus and Neptune. At Uranus, it found a featureless, blue-green world tipped on its side, with a magnetic field wildly askew. At Neptune, it discovered supersonic winds racing through a deep blue atmosphere and, most stunningly, active geysers erupting from its moon Triton, a world so cold its surface is frozen nitrogen. Yet perhaps their most enduring gift was the transformation of Saturn from a ringed dot into a cosmic masterpiece. The Voyagers flew through the ring plane, revealing it to be not a few solid bands, but hundreds of thousands of individual strands, braided, kinked, and shepherded by tiny moonlets. They showed us that rings are not ancient relics, but dynamic, evolving structures, a ballet of ice and dust on a scale beyond human comprehension. These missions redefined our neighborhood, turning points of light into places with weather, geology, and profound mystery. But their work was far from over. Having completed their planetary mission, the twins set their sights on a far more distant horizon, the edge of our sun's domain. For decades, they have sailed outward, their nuclear power sources slowly fading, their instruments one by one falling silent to conserve energy. Their final and perhaps most profound task is to find the boundary. They have become our scouts at the frontier, measuring the particles and magnetic fields where the solar wind, the constant stream of charged particles from our sun, finally meets the cold, dense interstellar medium, the gas and dust that fills the space between stars. Voyager 1 crossed this turbulent zone, the heliopause in 2012, Voyager 2 followed in 2018. They are now in interstellar space, the first human-made objects to enter the galactic ocean. Each week, they still phone home, sending back data about this uncharted territory, a faint signal that takes over 20 hours to travel at the speed of light to reach our antennas. Their messages describe the increased density of plasma, the shift in magnetic field direction, the cosmic rays from distant supernovae that are no longer held back by the sun's protective bubble. They are sampling the galaxy itself, and aboard each spacecraft, bolted to its side, is a time capsule for any finder that might exist in the vast, silent eons ahead. The golden records, these are not digital files, but analog phonograph records made of gold-plated copper, carrying the sounds and images of Earth. They contain greetings in 55 languages, the brainwaves of a person in love, music from Bach to Chuck Berry, the sounds of surf and thunder, and 115 images encoded in analog form, from diagrams of DNA to photographs of people from around the world. They are a message in a bottle cast into the cosmic sea, bearing witness that on a small blue world, a species once looked up, built machines, and dared to send its story sailing into the night. Long after their last transmitter falls silent, the Voyagers will continue their endless voyage, silent arcs carrying the whispers of a planet that dreamed of the stars. To understand the most violent forces in the universe, we must learn to see in a new light. X-rays are the high-energy signature of cosmic chaos, emitted from places where matter is torn apart, crushed to unimaginable densities, or heated to millions of degrees. For decades, telescopes have captured these X-rays, telling us about the temperature and composition of their sources. But a crucial piece of information has been missing: the orientation or polarization of those light waves. This is the specialized mission of NASA Imaging X-ray Polarimetry Explorer, or IXP. By measuring how these high-energy photons are aligned as they travel through space, IXP acts as a cosmic forensic tool, revealing the hidden structure of magnetic fields and the geometry of matter in the most extreme environments we know. Think of ordinary light as a crowd of people walking in every direction. Polarized light is like that same crowd, now marching in perfect, synchronized rows. In the cosmic realm, the processes that create X-rays often align these waves in specific patterns, and that pattern holds a story. When X-rays are produced in the intense magnetic field around a neutron star or a black hole, their polarization is directly imprinted by the field's shape and strength. By reading this imprint, IXP can map magnetic fields in places we can never visit, allowing scientists to see the invisible architecture that controls how these monsters consume matter and blast energy across the galaxy. One of IXP's primary targets is the Crab Nebula, the expanding wreckage of a supernova witnessed on Earth in the year 1054. At its heart spins a pulsar, a city-sized neutron star rotating 30 times per second, with a magnetic field a trillion times stronger than Earth's. IXP observations of the Crab provided a landmark discovery, the highest degree of X-ray polarization ever measured from an astronomical object. This told scientists that the X-rays are coming from a remarkably ordered region near the pulsar, likely from powerful jets of particles being flung outward along its magnetic poles. It confirmed that the nebula is not just a chaotic cloud, but a highly structured engine, with its magnetic field acting as a focused cannon. The mission is also peering into the surroundings of black holes, both the stellar mass variety and the supermassive giants at galactic centers. As matter spirals into a black hole's accretion disk, it becomes superheated and emits X-rays. The polarization of these X-rays can reveal the tilt and spin of the inner disk, and even the mind-bending effects of gravity warping spacetime itself. In the supermassive black hole at the center of galaxy Markarian 501, IXP data suggested that the X-rays are reflected off the accretion disk, a finding that helps astronomers piece together the three-dimensional shape of this violent feeding process. Each measurement is like adding a dimension to a flat picture, transforming a blur of light into a precise, dynamic model of physics at the edge of possibility. From the shattered remains of exploded stars to the particle jets screaming from active galaxies, IXP is providing a new diagnostic tool for the cosmos's most energetic phenomena. It asks not just what these objects are made of, but how they are built and how they operate. This shift from simple observation to detailed physical understanding is turning theoretical sketches into blueprints, showing us the precise mechanics of the universe's most powerful engines. But to move from hints and shadows to a portrait, we need a new kind of eye. The ultimate goal is not to infer an atmosphere from a chemical barcode, but to see the world itself. This is the dream behind NASA's most ambitious future concept, a mission that would redefine our place in the cosmos, the Habitable Worlds Observatory. Envisioned for launch in the 2040s, this would be the first space telescope designed with one explicit, staggering purpose: to directly image and analyze an Earth-like planet orbiting a Sun-like star. The challenge is one of cosmic contrast. Imagine trying to see a firefly hovering next to a searchlight from thousands of miles away. An Earth-sized planet is billions of times fainter than its host star and lost in its blinding glare. The Habitable Worlds Observatory would solve this with an instrument of exquisite precision, a coronagraph or perhaps a starshade. A coronagraph is a complex internal mask within the telescope that blocks the star's light with near-perfect accuracy, allowing the faint dot of the planet to emerge. A starshade is a separate, sunflower-shaped spacecraft flying tens of thousands of kilometers in front of the telescope, perfectly positioned to cast a deep shadow over the star, leaving the planet visible in the surrounding dark. Either technology would be an engineering marvel of unprecedented stability and control. The reward for this monumental effort would be a revolution. For the first time, we would not be studying a data point, but a place. The telescope would capture the actual reflected light of another pale blue dot. By splitting that faint glow into a spectrum, scientists could search for the definitive signs of a living world. The presence of large amounts of liquid water would be indicated by a specific glint, a signature of oceans. The reflection spectrum could reveal surface features, suggesting the rough texture of continents versus the smooth sheen of seas. Most critically, it would analyze the atmosphere with a clarity far beyond anything possible today. It would hunt for the strong, simultaneous presence of oxygen, methane, and perhaps even the subtle traces of chlorophyll or other pigments. Finding this combination would be the closest thing to a confirmation of life we could achieve from light years away. It would tell us that the planet is not just potentially habitable, but inhabited, a world where biology has reshaped the entire atmosphere. This single image, this first family portrait of another Earth, would be an answer to the oldest question. It would tell us that planets like ours are not just possible, but that they are alive. The Habitable Worlds Observatory is the logical, breathtaking culmination of every mission that came before it. The moment we stop guessing about other Earths and finally meet one. These 30 missions form a single, breathtaking question posed to the universe. Each one is a master key, designed to unlock a specific, fundamental mystery that has haunted our species since we first looked up. They ask where we came from by probing the raw metal heart of a protoplanet and the icy fossils of the outer solar system. They ask if we are alone by tasting the plumes of ocean moons and reading the chemical stories of distant sunsets. They ask what the cosmos is made of by mapping the invisible dark matter web and listening for the echoes of colliding black holes. And they ask where we are going by building the first outposts on another world and testing the sails that could one day carry us to the stars. This is not a scattered wish list. This is a coordinated, generational campaign of discovery, humanity's collective curiosity reaching out as a single, determined hand into the void. Every launch, every data transmission, every image from a new world is a sentence in a story we are writing together. The most profound revelation from all of this may not be about alien oceans or cosmic inflation. It may be about us. In striving to touch these distant horizons, we are forced to invent, to cooperate, to push the boundaries of our own ingenuity and compassion. We discover not just new worlds, but new capabilities within ourselves. So stay curious. Follow these missions as they unfold over the coming years and decades. Watch as the pictures come back, as the mysteries slowly yield their secrets. Because in exploring the grandest questions of space, we are, in the end, exploring the deepest truths of what it means to be human, alive, and awake in a universe of limitless